Our next application of integration deals with this type of a figure, and a way to think of this is like a piece of pipe. We have the circle outside is hollowed out in the middle, and it is of a certain height or length, if you will. And so this is a piece of pipe, and the question is, what is the volume of this piece of piping? Now, what I have labeled here are some radii. Lowercase r is the inner radius of the hole that's been cut out of the center of the pipe. Capital R is the outside radius of the pipe. And I've introduced this notation. This is the Greek letter rho. It's lowercase rho, Greek letter. And rho is the distance from the center to the midpoint of the thickness of the pipe. And so it turns out that it's not very challenging to see that rho is the average of the outer and the inner radius. And so I'm going to write rho to be r plus capital R plus r, little r, all over 2. And then we can rewrite this expression, if we like, as 2 times rho is equal to capital R plus r. Now the question we want to ask is, what is the volume of this piece of pipe? And we're going to use this later on in our computation of volumes of solids of revolution. But for now, all we're after is, what is the volume of this piece of pipe? Well, it's pretty straightforward. If we didn't have the hollowed out part, we would simply have a cylinder. And so we know the volume of that cylinder. We know the volume of the cylinder is pi times the radius of the entire cylinder. That would be the entire outer radius squared times the height, or the length, if you will. Now, but what we're going to do, we actually, when we think of a piece of piping, we actually drill out that solid so we have this edge, or we have this thickness, and so that goes all the way through to the bottom of the piping. And so we've drilled that out. So if we subtract from this amount the volume of the hole, well, what is that? That's pi times the inner radius, which is lowercase r, squared, times the height. We subtract that off, that gives us the volume of this piece of piping. Just the metal, if we think of that as a metal piece of pipe. Now, what we're going to do next is throw some algebra at this. What I'm going to show you here is not something you need to be able to develop. You do not need to be able to reproduce this. But I'm going to show you where this formula comes from so that when we use it to find our volumes, it does make sense that this actually is giving us what we say it is. So what we're going to do is do some algebra here. Factor the pi to the front of the expression. This is r squared minus cap r squared minus little r squared. And I'm going to throw h out the tail end here. This is the difference of two squares, and we know that factors. Again, you do not need to be able to reproduce this. This is not something that you would actually construct. But for the record, here it is. This is r plus cap r plus little r, cap r minus little r. That's just difference of squares from your glory days in basic algebra. And now I'm going to rearrange this expression. This is cap r times, this is the sum, times h. I'm going to multiply this out the tail. This is 1, 2, 3, 4 numbers multiplied together. We can multiply in any order we like. And now we can rename this. I know what cap r plus little r is. That's 2 times rho. Pi times 2 times the rho. And we call this the Greek letter rho. This is the average radius, the radius at the center of this piece of piping. All right? The center. That's what rho represents, the radius to the center. Times h. And now what is capital R minus little r? Well, what we're going to do is we're going to create this picture by partitioning the axis. And so it's going to turn out that this value, cap r minus little r, that is the thickness of this, and that's going to, if we're going to see this, that's going to be delta x, where that is, we can think of that as being the representation of the thickness of this pipe. And then if you rearrange this expression, the volume is 2 pi times rho. Now, typically, that radius will be a function of x. The distance from here to here will be some function of x. So I'm going to write this as rho of x. It's very often, in fact, most often, it's an extremely simple function of x, but it is, in strictest case, a function of x. And then height is also going to be a function of x. And this is the partition of x. And so this is the volume of one of these pieces of piping. Now, we introduce a new piece of terminology. This is not called a piece of pipe. It's called a shell. And what we're going to talk about is finding volumes of solids of revolution using the shell method, as opposed to the other day we talked about the disk or the washer method. So this is the shell method. The reason we have several ways to do this is certain problems, and we'll see this, certain problems lend themselves to one method or the other. Some problems, if you do the shell method, it's relatively straightforward. It can be done with a single integral. Whereas if you try to do the same problem with the disk or the washer method, it might not be feasible because of some solving issue. It might not be feasible because the integral you generate might not be as easy or as straightforward an integral, or you might simply just generate two larger integrals. And sometimes it works the other way around. Sometimes the shell method is more challenging, but the disk method is easier. And so having an understanding of both of these methods is important for this process. So that's the introduction to this notion of the shells. Now, the next piece is this. Suppose I take that curve, call this y equals f of x, and this is 0 to, let's call this 0 to, suppose this is 4. I'm picking a number out of the blue sky. That's 4. And so we're bounded by the y-axis, the x-axis, the line x equals 4, and this function. Take that region and rotate it about the y-axis. Rotate this about the y-axis. And we're going to find that volume using something called the shell method. Now, when we do this, this is the key notion. With the shell method, the axis of partition is the other axis. Or the opposite axis. If you revolve about the y-axis, the axis of partition is the x-axis. When I say the other axis, what I mean is opposite of the axis of revolution. If you revolve about the y-axis, you partition the x-axis. If you revolve about the x-axis, if we were going to revolve this about the x-axis, then you would partition the y-axis. For the shell method, the axis of partition is opposite the axis of revolution. It's the other axis. For the disk method, and disk is the same as washer. Remember, washers are a special subcategory of disks. For the washer method, the axis is the same. For the disk method, the axis of partition is the same as the axis of revolution. If we were going to use the disk method, if we're going to revolve this about, say, the x-axis, for the disk method, if you revolve about the x-axis or any line parallel to the x-axis. If you revolve about the x-axis, then you partition the x-axis. For the shell method, if you revolve about the x-axis, then you partition the y-axis. It's extremely important that you get that piece correct right off the bat. So what we're going to do is, suppose we're going to revolve this about the y-axis, and suppose we're going to use the shell method. So we're using the shell method. For now, why that's advantageous, we'll kick that can down the road. But for now, let's assume we're going to use the shell method to find the volume of the solid of revolution form by rotating this region about the y-axis. We're using the shell method. The axis of partition is the opposite axis. We revolve about the y, so we partition the x. That's important because what this tells us right off the bat is no matter what else happens, we know it's dx, which means everything in here needs to be a function of x. And if it is not a function of x, you need to fix that. Back solve to make it function of x. If we were going to revolve about the x-axis, then you would partition the y-axis, and then you would be using dy, which means everything in here needs to be a function of y. Knowing the axis of partition is absolute bedrock. Once you establish the axis of partition, that tells you the variable of the integral, and now you can start to find your footing and be able to make some headway out of this. All right, so we have that. We know we're partitioning the x-axis. Now, the way to think of it is this. Take, let's say, this rectangle. If I rotate just that piece, if I take a rectangle, think of this chalk as being a rectangle. If I rotate that chalk about an axis, what I'm sweeping out in 3 dimensions is a piece of pipe. If you rotate this about the axis, you will generate a hollowed out piece of pipe. This piece will rotate and nothing inside here will get swept out. You will generate one of these pieces of piping. All right? And so then if you took the next rectangle over, right? What this looks like is sort of like a soda koozie, or this is like the cloth that you wrap around pipes to keep them warm in the winter. If you lived where you needed to have pipes warmed in the winter. But if I rotate this green, it would make a slightly larger radius and slightly shorter height, a similar piece of piping. And it would look something like this. And that would be slightly larger than the red. It would have this red inside of it. So do we see what's happening? And then, if we take this next one over, this one is blue, and rotate it, that would give us another slightly larger piece of piping. And if we rotate the next one over, let's suppose it's this white one now, then that would be a slightly larger. It's sort of like a birthday cake, but it actually is a collection of pipes that have been nested in here, because this red goes all the way down, this green goes all the way down, this blue goes all the way down. And if we do that for all of this region, then what we can say is, if we want to find the volume of that solid, if we rotate the entire piece. Now we've left out little fiddly bits here on the end, but the volume of the solid we want is approximately equal to the sum of all the volumes of these pieces. And so if we take the volume of any one of them and then add all those up, that gives us an approximation of the volume of the entire region. And if we take the limit, is it clear? As these get thinner and thinner, these little leftover bits get smaller and smaller. The accuracy increases. And as we take the limit, that is actually what we define to be the volume of this solid of revolution. So the question is, what is the setup? Well, it comes from right here. So what we're going to do is I'm going to back up the picture here. And I'm going to go back and take just one of these. Let's take just the blue one. So here's my figure. Just the blue rectangle. All right. That's the piece I'm going to revolve about to form this pipe. Well, when you revolve, you generate that piece of piping, right? Right, in 3 dimensions. It's hollowed out on the inside. So what is the volume of that? Well, we use this to establish this. First off, the multiplier, using the shell method, the multiplier is 2 pi because of the algebra that led us to this expression. With the disk or the washer method, the multiplier is pi. With the shell method, it is 2 pi. That's a fundamental difference. Then we need the radius function, the radius. We need to know the distance from the center to the center of this rectangle. Well, we know what that is. That is the x value. We see that? That is the x value. When we partition this, whenever you form a partition, you choose a value. I'm choosing the center value, and that is the x value. Anytime you're revolving about the y-axis, that radius is simply the x-coordinate. Now, if you revolve about a different axis, things can get different. But if you're revolving about the y-axis, you can take that to the bank, revolve about the y-axis, the radius is the x-coordinate. So, 2 pi, got that. The radius, that's the x-coordinate. Now I need the height. I need the height, which is that distance. This is the height function. Well, the height changes depending upon where you are. But I know what this height is. That distance is the function value. Right? More generally, it is the top minus the bottom. It's just the bottom happens to be 0. So in this particular case, that height is simply the function value. Now suppose, don't change what you've written here, but suppose we have a slightly different piece. We have a y equals f of x for the top and a y equals g of x for the bottom. Now, what is the height of this blue rectangle? It is the top curve minus the bottom curve. So the height is always the top minus the bottom. All right? Now, in our particular given problem, the bottom is actually the axis, which is to say the bottom is 0. So we don't need to subtract that off. We can just have the f. So in this particular case, the height is f of x. It's not necessarily f of x. The way to think of this is top minus bottom. Right? And the last piece we need are the limits of integration. Well, the limits of integration are the endpoints of the partition. And that's why you need to know what axis is being partitioned at the very start of the problem. That tells you the limits of integration, which is 0 to 4. And we're out. If all you're asked to do is set up the integral, that integral is now set up. If you were given a specific function here, you would plug in that specific function, and that's the integral that finds this using the shell method.